last time we talked about impulse response and step response. In addition to those, we talked about their relations. In this lecture, we will let's quickly remember what we have discovered about step response and impulse response, and also we will say a few words about the ramp response. So this is a short summary of last time. Okay, we dealt with the following RC circuit. Okay, let this be the input. This is our output, the capacitor voltage. This is the LTI resistor. Okay. We're always, by definition, when we're dealing with impulse response and step response, dealing with the zero state response case. Therefore, by definition, the initial condition is zero. Now, the differential equation describing this system is dVc plus 1 over RC. Vc equals 1 over RC times the input. Okay. And then when the input is unit impulse function, then what you get at the output is called the impulse response. Okay. So impulse response was, first of all, we denoted it by h of t, and by definition, impulse response is such that the input is unit impulse and all initial conditions are set to zero. And we obtain the solution using two different approaches. To be 1 over RC to the minus T over RC, then that's multiplied by the step function. We also talked about the step response. Where, by definition, this time we are applying from the input unit step function, again under the assumption that all the initial conditions are zero. The notation that we used for step response was S of t. So by definition, the input is unit step, and all initial conditions are zero. Okay, and for that situation, we obtain the solution. Which was 1 minus T over RC, then everything multiplied by U of t. And also we discovered that since the impulse function is derivative of the step function, it turned out that the step response, or the impulse response, turned out to be the derivative of step response. Okay, or you can just talk about the reverse relation. That is, the step response is the integral of the impulse response. Yeah. So, since unit step is the integral of the impulse function, delta tau d tau, thanks to that the circuit is LTI, we have step response equals minus infinity to t. And then we're integrating the impulse response h tau e tau, and that yields minus t over rc u of t, which is our step response. Okay. Once again, step response can be obtained through integration from impulse response, or impulse response can be obtained from the step response through differentiation. Now let's extend that observation to ramp response also. Okay. Now, I don't know if there's a universal notation for ramp response, so I will just denoted by this, and this is not P, it's supposed to be rho to Greek letter, okay? But it doesn't matter what you see that. And by definition, ramp response is such that from the input we apply unit ramp function, which is TUT, that is 0 for all negative times, and starting from 0 forward, it climbs with unity slope. And again, by definition, it's a zero state response. All the initial conditions are set to 0. Now, by using the relation between unit step and unit ramp, okay, the derivative or integral relation between unit step and unit ramp, we can obtain the ramp response from step response. Okay. Now, TUT, unit ramp, can be obtained easily by taking the integral of unit step. In other words, we have this relation, okay, U tau eta. Okay. And that suggests that ramp response to this input can be obtained by integrating response to unit step or the step response. Okay. That is rho of t should equal from minus infinity to t s tau eta. That is the integral of step response. Now the question is, what's the result of this integration? So let's do that. Let's integrate the step response, because we already have we already have obtained step response, and figure out what rho of t should be the ramp response. Then we can also obtain the ramp response directly by solving the differential equation, and then we can compare whether two solutions match, which they should. Okay, so let's compute ramp response first through integration. Okay, let's approach the problem in a region by region analysis. Okay. Method. Okay. So for t negative, okay, so we're talking about now this integration. For t negative, we're talking about integration from minus infinity to some negative number. And let's look at integrand. We're integrating this. Since everything is multiplied by u of t, and u of t is 0 for negative times, therefore integration from minus infinity to any negative time is 0. Hence, we have the ramp response is 0 for t negative. Okay, so let's put this aside as equation 1. Then for t greater than or equal to 0, we can write ramp response equals from 0 to t 1 minus e to d minus tau over rc d tau. Now that we no longer have to write this step function multiplying 1 minus e to the minus t over rc, because we're integrating from 0 toward future, and u of t is 1, okay, in that region, because we don't have to write it down. So let's compute this integral. So this equals tau plus rc e to the minus tau over rc. Okay, so that's the, and we evaluate it from tau equals t to tau equals 0. And that yields t plus rc e to the minus t over rc minus rc. Okay. So let's call this equation 2. So for t negative, rho of t is 0, the ramp response. For t positive, rho of t is this, the ramp response. Therefore, we can combine 1 and 2 using step function u of t and write it as a single expression. So let's do that. 1 and 2 together imply that the ramp response rho of t equals t plus rc e to the minus t over rc minus 1, everything multiplied by to the next step, u of t. And let's call this equation. So we obtain ramp response by integrating step response. We don't have to deal with the circuit, we don't have to deal with the differential equation. Under the assumption that we already have step response, we can easily obtain ramp response by integration. Now let's verify equation 3. This time, we will not bother with the step response, we will directly use the circuit over, in other words, the differential equation. Okay, now what we're doing is we're verifying this equation, okay, this time using the differential equation. Now, for t negative, everything is 0, and for t positive, what we have is, from the input, the voltage provided by the voltage source is increasing with unit slope, starting from 0. Okay, so the voltage is t. So that means the right-hand side of our differential equation is t over rc. Okay, 1 over rc times t. Okay, so that means that the input is ramp function. Now let's obtain the solution for this differential equation. We have the differential equation, we also have the initial condition, which is 0 by definition of ramp response. Okay. We have the differential equation, we have the initial condition, therefore we should be able to figure out the solution. Now this is an unhomogeneous differential equation. The right hand side is a polynomial of degree 1 in time. Therefore the particle solution will be also a polynomial of degree 1. Okay. So we're going to figure out the particle solution directly using the differential equation. And then we also have the homogeneous part, the homogeneous solution. And for the homogeneous solution, we just look at the left-hand side. The natural frequency is at minus 1 over rc. Therefore, the homogeneous solution will have the form some constant times e to the minus t over rc. Then we're going to combine the particle solution and the homogeneous solution, obtain the overall solution, and to that, at the final point, we apply the initial condition constraint, which in this case is 0. And that will give us the unknown in the homogeneous solution, and we will have obtained a complete solution. So let's do that. The particle solution should be a polynomial of degree 1. Therefore, we're talking about of this form, a plus bt. To figure out a and b, what we do is we take our candidate and put it into the differential equation. So let's do that. D a plus bt plus 1 over rc a plus bt equals 1 over rc times t. Then we have, if you differentiate this a disappears, we have b here. Okay. And then we have a over rc, another constant term. Okay. And then we have only b over rc t term for the first order terms. b over rc. This is plus. V over RCT, and the right hand side is 1 over RCT. Since this equation should hold for all times, clearly this must be 0, and here V over RC must be 1 over RC. Okay. This tells us that B must be 1 and A must be minus RC. B equals 1 and A equals minus RC. Therefore, we have figured out the particular solution. So, the particular solution is T minus RC. Okay, B is 1 and A is minus RC. And homogeneous solution is, because the natural frequency at minus 1 over RC is K times e to the minus T over RC. K times e to the minus T over RC. If you combine the two, you obtain the overall solution. Okay, let's do that. Vc of t equals Vht plus Vpt. That's K e to the minus T over RC plus T minus RC. We apply initial condition constraint. Okay, because by definition of ramp response, the initial condition is 0. Vc0 equals 0 implies what? Plugging t equals 0, this term disappears, and we have, and this term becomes 1, we have K minus RC equals 0, therefore K must be RC. K equals RC. Now at this stage, everything is known, and we can write the overall solution. Hence, Vct, which we computed to be the ramp response of the RC circuit, equals T plus RC e to the minus T over RC. Minus RC. For T positive, for T negative is 0, hence you multiply everything by unit step. Now that this is equal to 3, therefore we have verified what we wanted to verify. Okay. Now let's talk about a type of input that we haven't so far considered, which is the exponential input. In a sense, we did consider, without maybe knowing that we are considering exponential input, when we considered the sinusoidal input, okay? Because the sinusoidal, in the sinusoidal function can be written as sum of or linear combination of complex exponentials. Okay, but now we're talking about the real case. For example, exponential. So let's see how we obtain the solution when the input applied from voltage source or independent voltage source or independent current source, whatever our input is, to the circuit is of exponential character. Consider this circuit. Can be S. 3 ohms, 1.6 farads. And our output of interest is capacitor voltage, suppose. Now, we're given the following. The initial condition is that it's 6 volts, plus voltage is 6 volts, and the input or the voltage provided by the independent voltage source is of the following form: e to the alpha t volts. Okay, and alpha is a real number. Find capacitor voltage, find a solution for the following two cases. A, when alpha equals -3, alpha is that exponent in our input, and B, when alpha equals -2. Okay, so let's go through the solution. The differential equation describing the evolution of capacitor voltage. By now we know by heart it is 1/RC VC plus 1/RC equals 1/RC times D. Okay. And now, in this example, we're considering this particular type of input, e to the alpha t. Now, for R equals 3 and C equals 1/6, we have dVC plus 2VC equals 2 times Vs, and Vs is e to the alpha t volts. Okay. The natural frequency of this circuit is at -2, which is, well, -1/RC. -1/RC, and that's -2 for this case. Okay, now let's deal with A. Where alpha equals -3. So the differential equation now becomes 2VC equals 2e to the -3t. Again, we have a differential equation, okay, first order, non-homogeneous, and the right hand side is of this exponential form. Usually when we have a non-homogeneous differential equation, what we do is we separate the solution to two parts. We first deal with the particle solution, and then we figure out the homogeneous solution, combine the two, and obtain and apply to that combination the initial condition constraint. And in this case, it's VC0 equals 6 volts, and from there obtain the overall or complete solution. And how we pick the particle solution, or what the particle solution is in general. Well, so far we consider the constant input, and the ramp input we consider the sinusoidal input, and usually the rule of thumb was that the particle solution has the same form as the input or the right hand side. Okay, if the right hand side is constant, then the particle solution is constant. If the right hand side is a first order polynomial, the particle solution is first order polynomial. If the right hand side is sinusoidal with some frequency omega, then the particle solution is also a sinusoidal function with frequency omega. So let's carry that reasoning, or extend that reasoning to this example. The right hand side is exponential of e to the -3t. Therefore, a good guess for the particle solution would be that it also has the same form, some constant times e to the -3t. And to find that constant, what we will do is we will use the differential equation. So the particle solution is something times e to the -3t, whereas the homogeneous solution is, we look at the natural frequency or the left hand side, which is -2, is k times e to the minus 2t. Okay. So this plus that gives us the overall solution, and we have two unknowns, a and k. How do we find those two unknowns? To find a from the particle solution, we take the particle solution and put it into the differential equation, and that will tell us what a should be. For k, what we do is we sum particle solution homogeneous solution, and to that sum we apply the initial condition constraint, and that will give us k. So let's do that and obtain the solution. dvp plus 2vp equals 2e to the minus 3t. Our particle solution is here, so what we have is minus 3a e to the minus 3t plus 2a e to the minus 3t equals 2e to the minus 3t. Now we can just remove e to the minus 3t's, okay, it's never 0. And that tells us that minus a should equal 2, hence a is minus 2. Okay, so the particle solution is found. Then the solution is VHT plus VPT, homogeneous plus particle solutions. That's k e to the minus 2t minus 2e to the minus 3t. What's the scale? We use the initial condition constraint to figure out that k. Plug in t equals 0 into the complete solution. This becomes k minus 2, and k minus 2 must equal 6. Therefore, k is 8. K must be 8. Hence, the overall solution for the capacitor voltage is minus 2t minus 2e to the minus 3t for t greater than or equal to 0. Okay, so that was A. For B, now we're going to work with different alpha. It may seem that it would just be a boring repetition of what we did in part A, but this alpha is not an arbitrary alpha in the sense that it coincides with the natural frequencies. Okay? That would require a slightly different treatment than how we approach the problem here. Now is e to the minus 2t volts. The differential equation is 2e to the minus 2t, and since alpha coincides with the natural frequency at s equals minus 2, the particular solution cannot be a times e to the minus 2t. It cannot have the direct form of the right hand side. Okay. Well, you can always try something times e to the minus 2t. If you do that, since it matches minus 2 is the natural frequency of the circuit, d v plus 2v for that candidate will just give you 0 regardless of a. Okay, so what you obtain is therefore 0 equals something non-zero. Therefore, that's that will not clearly help you. That means particle solution is cannot be of the form that's Vpt equals some constant times e to the minus 2t. Okay. So when the alpha, let's say the exponent of the right hand side matches or coincides with the natural frequency, what you do, it turns out, instead of a e to the minus 2t, what you have to do is you have to introduce also this first order term t. Okay? So the particle solution must have that form. So let's work out what a is in that case. dvp plus 2vp equals 2e to the minus 2t. So that implies the derivative of that candidate is a e to the minus 2t minus 2a t e to the minus 2t, okay, plus 2at to the minus 2t equals 2e to the minus 2t. Okay. Now this term cancels with that, and what we have is a e to the minus 2t equals 2 times e to the minus 2t, therefore a must be 2. Okay, a equals 2. Now, the particle solution is still the same, or the form of the particle solution is the same. Now we combine particle solution and homogeneous solution and write the overall solution. VHT plus VPT, and in this case we have k e to the minus 2t plus 2t e to the minus 2t. And to find k, again we use the initial condition constraint. VC0 must be 6 volts. If you plug in t equals 0, particle solution disappears, and what we have is k equals 6. K equals 6. Therefore, the overall solution for this case is 6 plus 2t times e to the minus 2t. So, once again, we have to be careful when the exponent of the right hand side, the input, coincides with one of the natural frequencies of the circuit.